Okay, please turn to page 25 of your note packet so I can go over conditional probability and independence, which is section 5.3. Read along with me. The conditional probability that an event happens, given that one has already known to be happening, is called conditional probability. The probability that event B happens given that event A has happened is denoted by the probability of B given A. In this notation, you'll notice that the event B is the event whose probability we're looking for, while to the right of the vertical bar, A is considered the given event that has already occurred. This leads us to the definition of independent events. Events A and B are independent if the occurrence of one has no effect on the chance that the other will happen. So in the terms of conditional probability, the probability of A given B will equal A, because the fact that B has happened makes no difference if the events are independent. Likewise, in symbolic form, the probability of B given A will be equal to the probability of B. This particular definition and these symbols will be used in future problems as what I'm going to call a test for independence. So now dependent events are those such that when we know one event has or hasn't occurred, it influences the probability that the other event does or does not occur. Some examples below, like flipping a coin, rolling a die, and generating random digits, are considered independent events. The outcome on a coin, for example, if it turns up heads, when we flip again, the result on the next flip does not matter if the previous flip was heads or tails. Likewise on die rolling or generating digits. In the examples where we pick a marble out of a jar, draw a card from a deck, and select a name from a hat, if we repeat those tasks over and over, they would be considered independent as long as those repetitions are done with replacement. If those repetitions are done without replacement, then those particular repetitions will be considered dependent. To consider why these events are dependent, let's think about a deck of cards. If I pick a card from a deck and want to know that the chance that that card I pick is red, I would answer 26 out of 52. If I then take a second card but don't put that first card back, now the chance that the second card is red is 25 out of 51. That second probability we calculated is known as a conditional probability. Sampling without replacement leads to dependent events, and we're going to have to put conditional probability to use to find probabilities of outcomes like that. This idea of conditional probability has happened before. We worked in Chapter 1 on two-way tables, and in those tables, when we were asked to make conditional distributions for the row or column variable, we generated percentages for those distributions based on conditional probabilities to draw the side-by-side or segmented bar graphs. Please turn to page 26. These two examples deal with the Titanic. In this two-way table of data, you see, from the totals I filled in, that there are 1,207 passengers, and they are broken down by survival status and class of travel. To answer Part A, given that the person selected was in first class, what's the chance that they survived? We find that probability just from an appropriate numerator and denominator from the table. Given first class, we'd be talking about 319 people, and the probability of surviving would then be 197 out of 319. For Part B, given that the person selected survived, the chance that he or she was in third class would be found from the ratio of 151 out of 442. For the question below, Part A, find the probability of survived given the second class. Similar to the example above, survived given second class would be 94 out of 261. Part B, the chance of survived would equal 442 out of 1,207. I'm going to change these fractions to decimals for use in Part C. Part C asks me to use these answers to determine whether the events survived and second class or independent. Well, as I said about page 25, I can do this independence test by checking whether or not survived given second class equals the probability of survived. In other words, I need to know if, knowing that this person was in second class, the survival rate is the same as the survival rate overall. Well, we can see from Part A, where we already calculated the probability on the left to be 0.360, and the probability of survival is 0.366. Since these numbers are not exactly equal to each other, we conclude that the event survived and second class are dependent. Turn to page 27. Here's a two-way table of who eats breakfast, broken down by eating or not eating regularly and gender. If we find the probability asked for in 68A, the probability of being a breakfast eater given that a person is a male, we go into the two-way table of data and we grab a count for the numerator and denominator. So breakfast eater given male is going to be 190 out of 320. For Part B, we want the probability of male given breakfast eater. Given that I'm a breakfast eater, what is the chance of being male? So now I have 300 people who eat breakfast regularly. The chance of being male is 190. Notice that because the orders of the given event and the event you're looking for are switched here, we got two very different answers for these probability questions. In question 70, we are now asked whether or not events B and M are independent. So in that test for independence, I'm going to want to figure out if the probability of B given M is the same as the probability of B, meaning given that the gender is male, it has no impact on the probability of eating breakfast or not. So we have to work out these calculations on the left and right side of the equal sign. Breakfast given male was 190 out of 320. The probability of being a breakfast eater is 300 out of 595. Take a moment to compute these two probabilities in decimal form. Since 0.594 is not equal to 0.504, we conclude that the events B and M are not independent. B and M are not independent because the probability of B given M is not equal to the probability of B. Question 76. If we roll two fair six-sided dice, one red, one green, are the events sum is 8 and green die shows a 4 independent? Justify your answer. I'm going to take a moment to draw out the sample space, showing you all possibilities when you roll two dice. So there are 36 outcomes, as seen in my sample space chart here. The first number in the ordered pair would be presumed to be the result on the red die, and the second number in the ordered pairs are the result on the green die. And again, there are 36 equally likely outcomes in the sample space. So to answer this question, our sum is 8 and green die shows a 4 independent, we have to do that test for independence by figuring out the following. Sum is 8, given green is 4. We'd want to know if that's equal to the chance that the sum is 8. So sum is 8 given green die is a 4. We have to go in and find all the locations where the sum is 8. And that would happen in the ordered pair 2, 6, 3, 5, 4, 4, 5, 3, 6, 2. So if we just look at the right-hand side here, I see a 5 out of 36 chance that the sum is 8. And on the left side, given that the green die is a 4, the chance that the sum is 8 would only be this outcome, where the green die is a 4, showing that the sum is an 8. So now that is 1 out of the 5. So 1/5 is 0.2, while 5 out of 36 is equal to 0.139. And once again, since these two calculated probabilities are unequal, we would walk away thinking that the green die showing a 4 and the sum is 8 are not independent. Please turn to page 28. Well, now you saw me list out a sample space for rolling 2 dice. And in general, if we want to list out sample spaces, we can apply a multiplication principle. Or we could perhaps draw a tree diagram to help us list outcomes. This multiplication is a counting rule that states if you can do a task in n one ways and you can do a second task in n two ways, then both tasks can be done together in n1 times n2 ways. So the previous example I did would have a red die and green die, each of which has 6 outcomes, 6 possibilities. 6 multiplied by 6 got us to the 36 outcomes in the previous sample space. To demonstrate what we mean by a tree diagram, if I flip a coin 3 times, well, first, if I use the multiplication principle, I would have 3 flips. The first flip could have any one of 2 outcomes. The second flip could have any one of 2 outcomes. The third flip could have any one of 2 outcomes. So we should know before we even make a list that there are 8 outcomes in this sample space. Now if I draw a tree diagram, we should put down a little symbol here representing a coin or whatever we're working on, and it's a dot. From that dot we draw branches. The first set of branches is for the first flip where we can get a head or a tail. Now we're going to flip again, so following that first head we could get a head or a tail. Following a tail on the first flip, we could get a head or a tail. And then as we go to the third flip, we could get a head or a tail, a head or a tail, a head or tail, and then finally a head or a tail. When I look at the last branch, notice if I count here, I have 1, 2, 3, 4, 5, 6, 7, 8 leaves, and these 8 leaves would help me list out all of the outcomes in the sample space. Now to answer part A, find the probability that the first 2 flips lands on heads and the third flip is a tail. All I have to do is reason through that this is asking me for this outcome, HHT, and the HHT is on the diagram right here. And because these are 8 equally likely outcomes, we would just answer 1/8. In part B, find the probability that there's exactly 2 heads and 1 tail. Well, now I go through the sample space and I count every time that I meet this condition of exactly 2 heads and 1 tail. So there's 1 instance of it, a second instance of it right here, exactly 2 heads and 1 tail occurs in those 2, and this third one right here that I missed at the top. So when we write out this probability of exactly 2 heads and 1 tail, we get to give a simple answer of 3 out of 8. And the tree diagram there basically just kind of helped us organize that information. Okay, this definition at the bottom of page 28 lets us know that if we talk about the intersection of two events, A intersection B, we have a symbol here with this upside down U-shaped character for intersection, and this would imply that both event A and B occur. So we're going to talk about computing the probability for the probability of A and B. This is known as the general multiplication rule, and this general multiplication rule says if we want the probability that A and B occur, we take the probability of A multiplied by the probability of B given A. So here we need to use conditional probability. As a special case, if A and B happen to be independent, then we get a more basic multiplication rule that's on the top of the next page. Please turn to page 29. So here we have a special case of the multiplication rule for independent events. When A and B are independent, remember that the probability of B given A will just equal the probability of B. So now the multiplication rule reduces to this, that the probability of A intersected with B equals PA multiplied by PB. That leads us to an important concept to help you distinguish between the words independent and mutually exclusive. So two events with positive probability are letting me know that PA is something greater than 0, PB is something greater than 0. Well, if two events are mutually exclusive, we learned from a previous definition that P of A intersected with B equals 0. Well, now if I'm going to be independent, and I'm working with this test of independence here, that two events that are independent follow this multiplication rule, I would get 0 for the left side, but this would be unequal to PA times PB if these are both positive numbers. So the left side is 0, while the right side is a number greater than 0. Therefore, A and B are dependent. Mutually exclusive events are always dependent. On to my example here. If I have a jar with 4 red and 6 blue marbles, and I'm going to select 2 marbles from the jar with replacement and note their color, determine the probability I get 1 red and 1 blue. So let's think about the marbles in the jar, and I'm going to demonstrate how I could organize a tree diagram. So I'm going to pick a marble, and that marble will either be red or blue on the first pick, and then I'm going to grab a second time after replacing the first marble and either end up with a red or a blue. On the branches, we can put these probabilities. So in this scenario for red and blue, if there's 4 red and 6 blue, there's a total of 10. So 4/10 written on that branch, 6/10 written on this branch. Because I'm putting the marbles back, every time I mark down that I have red, I write 4/10, while blue we write 6/10. You notice on these branches that the probabilities sum to 1. So to compute 1 red and 1 blue marble, I go over here and I check off which tree branches correspond to 1 red and 1 blue, and that would be that one, or this one. So this probability of RB or BR, you're going to start training yourself that when you're doing OR problems you add, while when you're doing AND problems you multiply. So the symbol RB, red and blue, I take the probabilities of 4/10 and 6/10 and multiply them together. And then I put a plus sign for BR. Well, the BR outcome is 6/10 times 4/10. All I'm doing is the special case of independent events and following the so-called multiplication rule here. So this is 24 out of 100 plus 24 out of 100 to get me 48 out of 100. If I move to part B, notice that it now says that the marble selection is happening without replacement. So when we work without replacement, it's the same tree diagram, red or blue, with 4/10 and 6/10. But now when I go and offset these other branches, if I took a red marble out and didn't put it back, there's now only 9 marbles left in the jar, of which 3 are still red. Because I took a red one out, there's only 9 marbles in the jar, but 6 of them are still blue. And then down here with the reds and blues, if we took a blue marble out of the jar, we have 5 that are still blue out of the 9 remaining. Sorry, we have 6. Nope, my bad still. We have 4 out of 9 that are red, while we have only 5 out of 9 that are blue. So now when I go with the 1 red, 1 blue probability, I'm looking for these two outcomes, R, B, or B, R. And I go to those branches where I've written down the probabilities. Red and blue is 4/10 multiplied by 6/9 plus sign. And then B and R is 6/10 multiplied by 4/9. This gives me 24 out of 90 plus 24 out of 90 to get 48 out of 90. Please turn to page 30. Well, now we're going to talk about calculating conditional probability. And if we want the probability of event B, given that event A has happened, we use what we call a conditional probability formula. And it goes like this. This formula is in our AP Stat formula booklet, that to find the probability of B given A, we take the probability of A intersected with B over the probability of A. Let me demonstrate that with the use of a sample space or Venn diagram. So in a Venn diagram, if there are 2 outcomes, A and B, and I know that event A has happened, well, now I only need to talk about event A. I don't have to worry about the rest of the sample space. So what is the chance of event B occurring given that A has happened? Well, the only outcomes that match up with event B are there where I just shaded in red. The part I shaded in red is the intersection. That's the numerator of the conditional probability formula, while the denominator is the given event PA. Notice that there's a few important notes below. If you go to get that numerator, probability of A intersected with B, you should not use the multiplication rule, PA times B given A, because you're going to be basically working in circles if you do that. There's going to be some other way in the problem to compute that numerator. Note number 2, when you look at these conditional probability formulas and these multiplication rules, you'll see that we're generically using the symbols A and B, and it's up to you whether you want to call the given event A or the given event B or vice versa. And when you do so, just be careful to appropriately label the given event as the one to the right of the vertical bar. Whatever you put there is known as the given event, and the other event goes to the left of the vertical bar. What you put to the right of the vertical bar is the denominator in the conditional probability formula, and the numerator is always the intersection of the 2 letters that you used in the conditional probability statement. Problem 78. I'm going to draw a little picture here. I just received a shipment, so I have a giant box of 10,000 switches. And in this giant box of 10,000 switches, 1,000 of these are bad ones. That must mean 9,000 of these are good ones. So I am going to grab 2 switches from this box, one after the other. So that means pick 2 without replacement. And if I do this, I want to demonstrate with a tree diagram what could possibly happen in this chance process. Well, of course, I could pick on the first selection either a bad one or a good one. On the second selection, I could follow up with a bad one or good one. Now that's the tree diagram. If I want to find the probability that both switches are defective, that means 2 bad ones, so we would be looking for this. So I'm only going to fill in these branches. In order to get the probabilities onto these branches right here, the probability of a bad one on my first pick is 1,000 out of 10,000. And now the probability of a bad one on the second pick, if I took out a bad one, There's now only 999 bad ones left out of the 9,999 switches still in the shipment. So if I find the probability in part B that both are defective, I'm answering the probability of getting 2 bad switches. There's an implied and in between those letters. So it's the probability of a B multiplied by the probability of a B given a B. Those numbers are already there in the diagram as 1,000 over 10,000 multiplied by 999 over 9,999. And of course, when you solve these problems, you'll see decimal answers in the answer key. And now that you have that decimal answer, notice that there's a less than 1% chance of drawing out 2 bad ones on consecutive picks out of this box, while overall in the population of switches, 10% are bad. So be careful about attaching meaning to these, and notice that it would be very rare then to get 2 bad switches in a row drawn out of this box. On to page 31, problem 80. If 10% of adults belong to a health club, I'm going to summarize that information with pH equals 0.10. 40% of these health club members go to a club at least twice a week. So the probability of twice a week given that I'm a health club member is 0.40. What percent of all adults go to a health club at least twice a week? So that question just asked me for the probability of H and T. In order to do that, the multiplication rule says I can multiply the probability of H times the probability of T given H, and in general, when you're looking for an intersection, you will find yourself multiplying 2 probabilities together. I'm using the proper notation just to get you used to this. Getting to the answer 0.04 is very important. The notation I use along the way is just me modeling good practice. Number 82. We saw in an earlier example that 93% of teens are online and that 55% of online teens have posted a profile on a social networking site. Of online teens with a profile, 76% have placed comments on a blog. What percent of all teens have done all 3 things, essentially? So let's again summarize the given information. I've got the probability of being online at 0.93. The probability of posting a profile on a networking site, given that I'm online, is 0.55. And then the percent of people who place comments, given that they are online and social networking, is 0.76. So if I want the probability then of all teens who are online have a profile on a social network and comment, this multiplication rule extends to these 3 outcomes, and you just take the 0.93 times the 0.55 times the 0.76. How many places should you round your decimal answers to? You'll notice conventionally in probability, we keep about 4 digits here after the decimal just for some accuracy. On to page 32. This example asks us to synthesize a few of the rules that have gone by so far in this section. So voters in a large city are 40% white, 40% black, and 20% Hispanic. A mayoral candidate anticipates attracting 30% of white, 90% of black, and 50% Hispanic. Draw a tree diagram to represent the situation and answer what percent of the overall vote does the candidate expect to get. So here we have to draw the tree diagram, and it would look like this. First, we put down the outcomes for the racial division of the city of white, black, and Hispanic. We label it 0.40, 0.40, and 0.20. And now here's the mayoral candidate, in each of these races, showing you that he expects 30% of the white vote. So let's use V for vote and V complement for don't vote. If we expect 30%, we put 0.30 and therefore 0.70 for don't vote. What percent of blacks here? We have 90% of black vote expected, and therefore 10% who are not going to vote for this mayor. And then for the Hispanics, we have 50% of the Hispanic vote, and therefore 50% who won't vote. That's problem 84. What percent of the overall vote does the candidate expect to get? So what percent of the vote? Well, that vote is going to come from the breakdown of white and voting for the candidate, or black and voting for the candidate, or Hispanic and voting for the candidate. These can be found on those branches already. White and voting for the candidate, use the multiplication rule, 0.40 times 0.30, plus for the word or, black and voting for the candidate is 0.40 times 0.90, plus Hispanic and voting for the candidate, 0.20 times 0.50, answering in decimal form and simplifying. So we get 0.58 after crunching this out in our calculators. Problem 86. So now if the election described in exercise 84, if the candidate's predictions come true, what percent of her votes came from black voters? Write this as a conditional probability and use the definition of conditional probability. So if these predictions come true, what percent of her votes come from black voters? So problem 86, summarized in the notation for conditional probability, is asking the following. Given that the candidate got voted on, what is the proportion of votes that are black? So using the conditional probability formula, the numerator gets B intersected with V, the denominator gets P of V. B intersected with V is 0.40 times 0.90. The probability of V we just calculated to be 0.58. Simplifying this result, 0.36 divided by 0.58 equals 0.6207. So if that candidate gets voted into office, 62% of the votes received would have come from the black race in the city. On to page 33. Finally, to find the probability of at least one, keep in mind that at least one in the language of inequalities would mean one or more. That could be difficult to list out or quantify with probability, so think about the complement of at least one being none. So if I wanted to compute the probability of at least one, I could use the complement rule, therefore, and get 1 minus the probability of none. If I was thinking about a sample space of 3 children as an example, and asking you for the probability that at least one is a girl, it may be easier to think in terms of the complement. So the complement statement for in a family of 3 children, at least one is a girl, would be the following. In a family of 3 children, none are girls. So if I knew then that the chance of no girls is 1/8, the chance of at least one girl is very simply calculated out then as 7/8. Okay, now as we end this, certain probability problems are going to ask you to combine several of our basic rules. Please use care in labeling events and their probabilities as stated in a problem. Look out for words like and, which are going to mean multiply, or will mean add, and if then or given that will signal you to using conditional probabilities. Tree diagrams and Venn diagrams can help you organize multi-stage calculations, and to demonstrate that, I have an example here with as little context as possible to try to show you the use of a tree diagram and a Venn diagram. So first I have, suppose the probability of event A is 0.70. Let's summarize the given information here in red. If A occurs, the probability of B is 20%. On the other hand, if A does not occur, the probability of B is 0.60. Notice event A not occurring has the symbol A complement. If I summarize the given information in a tree diagram, it will help me answer the following question. Given that the event B occurs, find the probability that event A occurs. Okay, so here's the tree diagram. First, I'm going to observe whether A does or doesn't occur. The chance of A occurring is 0.70, so I can deduce on my own that 30% of the time A does not occur. Following A, I'm going to have event B, which either occurs or doesn't occur. And according to the given information in red, the probability of B given A is 0.20, and the probability of B given A complement is 0.60. Well, every time you draw these tree diagrams, you can deduce on your own that the probability of A given B complement will be 0.80. And over here, the probability of B complement given A complement will be 0.40, because these branches here will always sum to 1. And now if you let me, I'm going to have you realize that every one of these branches tells you about this sample space with two events A and B which both happen. A happens and B doesn't. A doesn't happen but B does. Or neither event happens. So if I wanted to compute any of these probabilities in this sample space, all you do is take the branches and multiply. And you're going to see when you get these products and add them all up, if this is a valid probability model and you haven't made any mistakes, this is all the possibilities in a sample space of two events. So you can put 0.14 here, 0.56, 0.18, and 0.12. And if you add this up, it should be exactly 1, aside from any rounding error. So now if you look at the question, we can now figure out the probability given that B has occurred. What is the chance of A? The conditional probability formula tells me to get A intersected B over B. The probability of A intersected with B is already answered above. That's that 0.14. P of B needs me to go to both branches where B occurred and sum those. 0.14 plus 0.18. So we end up with 0.14 over 0.32, which calculated out is 0.4375. Now if I want to put this information in a Venn diagram, I can take the two events A and B and draw circles. And I can show you that the four numbers that we put up here can all be placed appropriately in this Venn diagram as well. So those four numbers that are on the tree would appropriately go into this Venn diagram, and we can place them. A intersected with B is 0.14. A intersected with B complement is 0.56. A complement intersected with B is 0.18. And A complement B complement is 0.12. Those four probabilities go here. So now if you want to look at the same calculation and you had this information placed into a Venn diagram as opposed to just listed out next to the tree here, we can do the same probability calculation. Sorry, we're getting a little squished right here. But the probability of A given B expands out into the probability of A intersected with B over the probability of B. And notice your Venn diagram helps you figure out that the probability of B here in the denominator can be found with the sum of that spot on the left, A intersected with B, plus the spot on the right, which is A complement intersected with B. This expanded formula has an important name here. It's called Bayes' rule. For those mu alpha theta people, this is Bayes' rule or Bayes' theorem. So we'd have the same calculation we saw above, a 0.14 in the numerator and a sum of 0.14 and 0.18 in the denominator to come up with the 0.4375. Same answer. Please turn to page 34. I'm only going to do problem 89 here at the top. Just in time for Christmas, we have a string of lights with 20 lights on it. Lights are wired in series so that if any light fails, the whole string goes dark. Suppose it's known that each light has a probability of 0.02 of failing in a 3-year period, and all the lights fail independently of each other. Find the probability that the string of lights remains bright for 3 years. So string stays bright means all 20 lights work. So the only way the string stays bright is if all 20 lights work. And each light has a 0.02 chance of failing, so therefore it has a 0.98 chance of working. Because we can assume these are all independent of each other, we'd have this 0.98 multiplied by itself 20 times. So we have 0.98 to the 20th, which is 0.6676. So even with a only 0.202 or 2% chance of any light fails, there's only about a 67% chance that this string stays working for the 3 years that someone may own it. On to page 35, problem 100 at the bottom. So when you're researching and creating a test for a patient who has a certain medical condition, it's important to say test the testing device. So in this experiment, there are 1,000 patients available, of whom we're told in the context of the problem that 250 have a medical condition, so we call them positive for the medical condition, and 750 not positive. And then it goes on to say that when given the test, technicians correctly identified 240 of the 250 patients with the condition. So that means the test came up positive 240 times. Unfortunately, the test also came up positive 50 times when the patient didn't have the condition. So once you have those numbers filled in, you can organize the rest of this two-way table by subtraction, and we can put 290 for the total number of times the test came out positive. We can deduce on our own that the test came out negative the other 710 times if we need that information. Part A is simply asking for what are the false positive and false negative rates for the test. So the probability of false positives would be the 50 patients who came up positive in the 750 patients who don't have this disease. So we get a false positive rate of 6.67%. The false negative rate is those 10 patients who do have this condition, who came up as a negative test. So the false negative rate is 10 out of 250, or 4%. On to part B. Given that a patient got a test result that was positive, what is the probability that they have the condition? So we can answer that from our two-way table in part B here. Given that we have a positive test result, what is the chance that we are actually positive in this condition? So we have a numerator with a p given p over the probability of a positive test. Okay, scratch that. I just messed that up. All I need to do, since I summarized the information in the two-way table already, is to write down positive condition given positive test is simply the 240 people out of 290. Divide those numbers, and I have 0.8276. And if you put a little thought into this, that's actually not very high. Given that I got a positive test, there's really only an 82% chance that I have this condition. So you can see that even though it looked like the test had pretty low false positive and false negative rates at 6% and 4%, those numbers need to be minute in order to not worry patients, telling them that they've tested positive for a test, because now with these things or these rates, there's only an 82.76% chance that they have the actual condition.